Picture a rig floor at 2 a.m., 90 meters above the waterline. A driller nudges a joystick, and 11,000 feet below, a bit responds. That connection runs through every electrical system on the vessel. Every megawatt generated exists to drive a specific mechanical component in the drilling chain. This diagram shows the core mechanical layout. The derrick is the steel tower that takes the full hook load. Below it sits the drill floor and the rotary table, flanked by the heavy lifting equipment of the drawworks. Suspended inside that derrick is the top drive. It rotates the drill string to cut through rock while traveling vertically on rails as pipe enters or exits the hole. The mud pumps provide the primary defense against formation pressure. While they cool the bit and carry cuttings, they are also responsible for maintaining the mud weight required to prevent an uncontrolled well kick. The central engineering challenge of an offshore rig is safely converting massive fixed-frequency diesel power into precise mechanical control within a constrained marine environment. Designing an offshore power system begins with the vessel's footprint. The geography of the hull establishes the fixed constraints for every cable run and switch room long before the first generator is specified. On a semi-submersible rig, heavy generators and switchgear sit low in the pontoons to maintain stability against pitch and roll. This results in power running upward through the columns, creating relatively short vertical cable paths. A drill ship uses a fore-to-aft layout. Power must travel the entire length of the ship to reach the derrick, requiring exceptionally long cable runs that introduce voltage drops and demand water-cooled drives to survive the salt air. A jack-up rig stands on the seabed with its hull elevated out of the water. Because the hull area is small, switch rooms are densely packed, which creates a compact footprint but leaves little room for maintenance. These comparisons illustrate topological determinism, the reality that the vessel's physical hull dictates the internal electrical architecture. The electrical path starts with multiple diesel generator sets running in parallel to ensure redundancy and grid stability. Each alternator produces AC power, typically at 6.6 kilovolts. This feeds the high-voltage switchboard, routing energy to drilling and propulsion loads. From here, power branches into step-down transformers, dropping to a compatible input voltage for the drives. If these transformers are undersized, they throttle the drawworks performance, regardless of how advanced the motor is. The entire path must be sized as a single chain. This distribution chain delivers raw power to the threshold of the variable speed drive, where mechanical control begins. This diagram shows the internal architecture of a variable speed drive. Stage 1 is the rectifier. This diode bridge receives the fixed frequency AC from the transformer and converts it into a pulsating direct current. Stage 2 is the DC link. A bank of capacitors smooths that pulsating DC into a perfectly flat, stable DC bus. This link severs the connection between the ship's fixed grid and the motor's ultimate speed. In Stage 3, the inverter uses high-speed IGBT switches to chop that DC power into a new variable frequency AC waveform. This stage provides the actual RPM control. By rectifying, storing, and inverting power, the VSD provides absolute independent speed control without dragging down the vessel's primary power grid. Many legacy engineers assumed DC motors were required for low-speed, high-torque applications. The offshore drilling results proved otherwise. DC motors carry a maintenance penalty. They control speed using physical brushes and a copper commutator, wear items that require constant manual resurfacing, resulting in rig downtime. AC induction motors generate rotation via induced magnetic fields, with zero physical contact between the rotor and stator. This allows for a fully sealed structure that blocks out corrosive salt spray and drill floor mud. As this graph shows, the AC VSD's diode rectifier inherently maintains a high constant power factor across the entire speed range. This eliminates the need for massive reactive power compensation capacitor banks. The ultimate performance test for any offshore drive system is the drawworks, which must suspend hundreds of thousands of pounds of drill pipe. This chart shows the torque speed curve for an ABB drilling motor. Modern AC VSDs deliver 100% of their rated holding torque at exactly 0 RPM, preventing the load from creeping during stationary operations. AC systems moved the industry forward by removing catastrophic maintenance failure points while improving low-speed torque control. Beyond the individual motor, Engineers must arrange these drives into a larger architecture, choosing between single-drive and multi-drive topologies. In a single-drive topology, every motor has its own independent rectifier, DC link, and inverter. This prioritizes fault isolation. If one component fails, only that specific motor is affected. A multi-drive topology uses a shared approach. One massive rectifier and a common DC bus feed multiple independent inverters. This reduces footprint and cabling costs. But it introduces a vulnerability. A fault in the main rectifier will disable every motor on that bus. Architecting a rig is a balancing act between maximizing spatial efficiency and preventing single-point catastrophic failures. These topological decisions scale up to flagship projects, such as ultra-deep-water drillships requiring 90 megawatts of total installed power. An 11 kilovolt high-voltage backbone must orchestrate dozens of separate VSDs, balancing steady thruster loads for dynamic positioning against the violent power spikes of the drilling package. At this scale, engineers use multi-winding transformers to cancel out harmonic noise and fully water-cooled cabinets to manage the extreme heat density. The objective remains consistent, using the VSD to convert raw generation into precise zero-speed control.